This is the second of two videos covering the Computer Fundamentals Lecture 8 of the IES Information Technology course. This video will focus on protocols and specifically TCP/IP. Computers need an agreed set of rules to be able to communicate with each other. This set of rules is called a protocol. Just as there are different protocols for people meeting royalty or world leaders from different countries, there are a variety of protocols that work at a number of different layers in network communications. Some of them you've heard through this series of lectures, like Wi-Fi, Bluetooth, NFC, HTTP, FTP, and TCP/IP. TCP/IP is the most widely used protocol in computer networks. It's the protocol used to send data across the internet. TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. Let's break this protocol down to its two parts and discuss what each does in a little more detail. The IP part of the protocol is concerned mostly with giving each device on the network its own unique identifier. There are two IP standards, IPv4 and IPv6. The V in these names stands for version. When internet use began exploding with the advent of the World Wide Web, IP4 was the standard. In this version of IP, each address is made up of 4 sets of decimal numbers separated by dots, but the numbers only run from 0 to 255, giving 256, so that's 2 to the power 8 unique numbers for each part of the address. In IP version 6, an address is made up of 8 hexadecimal numbers separated by colons, as shown here. And the new version of IP was necessary as there were no new unique addresses available for the internet as of February 2011. Well, let's look at the numbers. IP version 4 supports 4 groups of 8 bits. This is 2 to the power 32, or about 4.3 billion addresses. But some IP addresses are reserved, like 127.0.0.1, which allows a user to establish an IP connection to the device being used by the user. There are other addresses reserved for local networks only, and many others reserved for reasons which go well beyond the scope of this subject's requirements. IP version 6 supports 8 groups of 16 bits, that is 2 to the power of 128, which is a very, very large number. Given the fact that this is 5 by 10 to the power 28 addresses for each person alive today, there is little chance the addresses will run out soon. The TCP part of this protocol is responsible for breaking the data to be sent into packets, adding a header with destination and origin addresses, the packet number, and the total number of packets, and also a footer with some error checking codes. Routers then decide where to send the data onto so that the packet moves towards its destination. TCP also reassembles the data at the destination computer. Now, TCP doesn't define a route that each packet must follow. Packets may travel many different paths to get to their destination. If a path is broken, then the packets can be routed around it. Similarly, if a link becomes congested for whatever reason, then packets can be routed along a different path. Packets need not arrive in the correct order, but all packets must arrive for TCP to be able to reassemble the data sent. Now, each packet sent requires the destination device to send an acknowledgement that it was received. This is known as an ACK. If a packet is not received in a given time, then the destination device might send a NACK, a not acknowledged response, or it might send nothing and the sending device will automatically resend the packet after a timeout period. This is beyond the scope of our course, but it's good to think about how this problem is worked through on a very basic level. There is another layer to this protocol that makes locating resources on the internet more human-friendly. This system is known as DNS, or the Domain Name System. Instead of having to remember the IP address of a website, we remember a domain name like www.google.com. DNS servers store a database of domain names and the IP addresses associated with it. Therefore, when we type in, say, www.foundationu.com into an internet browser, the DNS server tells TCP/IP to send the data to the IP address 203.15.61.3. Now, each domain name is made up of a series of labels separated by dots. The domain name makes up part of what is known as a Uniform Resource Locator, or URL. It's unique for each file or document on the internet. And there are three main parts of the URL: the protocol, the domain, and the file path. Generally, the protocol is HTTP, Hypertext Transfer Protocol, or HTTPS, Secure Hypertext Transfer Protocol. But it can be FTP or Mail-to or others. The file path is written as a directory path followed by a file name. So in the example shown, the file you are requesting, index.htm, is not in the top level of the directory substructure, but rather in a folder called About, and then in a subfolder called St. Lucia. If the file was in the top level of the directory structure, the URL would look like this. You'll note that there are arrows pointing to parts of the domain labelled TLD and ccTLD. TLD stands for Top Level Domain, and ccTLD stands for Country Code Top Level Domain. Top level domains were initially used to show what type of organisation owned the computer. There's a generic list of TLDs on the screen. There are also some example ccTLDs, but it's because of countries like Tuvalu, which has a ccTLD of .tv, and the government that sells .tv domains through a company it has a 20% stake in, as well as others like Montenegro, which has a ccTLD of .me. The list of TLDs is ever expanding to include ones like the one shown here. These generally don't require a ccTLD. So let's identify each of the parts of the following URL. HTTPS is the protocol. www.adelaide.edu.au is the domain. .edu is the TLD. .au is the ccTLD. Applied Maths is a folder, and Images is a subfolder. Logo.png is the resource. In this case, that's an image file that we want to load into the browser. That is the end of Computer Fundamentals Lecture 8.